Let us now turn to the shapes of elliptical galaxies. They're called ellipticals for a really good reason. Their projected surface brightness profiles look pretty close to ellipses. And here are two intensity maps, lines of equal surface brightness. In the image on the left, the little knots are actually stars in the foreground because their brightness gets measured too. And you can obviously see that elliptical galaxies really do like ellipses, although ellipticity may be changing as a function of radius. Generally, they tend to be a little rounder in the middle. Originally, people thought that ellipticity is due to rotational flattening. Elliptical galaxy spins, centrifugal force stretches it in two directions, orthogonal to the spin axis, but that turned out not to be the case. And more modern studies indicated that, in fact, ellipticals, first of all, don't rotate very much, and second, their shape is not due to rotation. It is due to the velocity anisotropy. As you would recall, the stars in elliptical galaxies move randomly, sort of like molecules in gas. That's why they call them pressure supported. But it's possible in a dynamical system like that velocity dispersion is different along x, y, and z axes. The galaxy may be a little hotter in one axis than the other. And so that means the stars will go further out along that axis, will be longer. And now we think that the shapes of elliptical galaxies are due entirely to this anisotropy. Their temperature, if you will, is different in different directions. We can use statistics of observed shapes to try to deproject what's going on. What's shown here in the histogram is the distribution of through ellipticities, three-dimensional ellipticities, if indeed ellipticals were simple, flattened, or elongated prolate ellipsoids. But in reality, they can have three axes and therefore two axis ratios, and that plays a little more complicated. So the simplest case is if they're really spherical. There aren't many galaxies like that. Another case is that if one axis is equal to another, and those are bigger than a third one, then it's a football, it's a prolate ellipsoid. On the other hand, if it's short, one axis is shorter and the other two are equal, we have oblate ellipsoid, flattened thing, flying saucer. And more generally, we have three axes of different shapes. So on average, the actual ratios are shown here. In fact, the ellipticals are fairly close to be oblate ellipsoids, flattened along one direction, but not perfectly so. In addition to the dynamical evidence for anisotropic velocities, which I'll show you in the next module, we can actually tell this from pictures themselves. And this is a little tricky to envision, but it works like this. If you look at the set of nested triaxial ellipsoids from some oblique angle, you will in fact see that their apparent projected major axis seems to move, rotate on the sky. And that is called the isophot twists that you can, again, see here, that you can look from same triaxial ellipsoid from different directions, and the regions of higher density will project in certain major axis direction, and lower densities you will see it from slightly different angle. Ellipse will look like if it's turning, and so that's exactly what's observed. Even in our immediate neighbor Andromeda galaxy, Andromeda has two dwarf elliptical companions, and if you stretch the picture at high contrast, you can see that for one of them, NGC 205, the outer isophotes are twisted and actually a little boxy, which is another interesting question. What's shown on the lower left is a set of isophotes for some elliptical galaxy, and major and minor axes are drawn. And you can see as you go to ever larger radii, the axes seem to rotate. So this is still elliptical shapes, but actually ellipticals are not purely elliptical in shape, pretty close, but not always exactly. And the first deviation that you can quantify is if there is an extra harmonic, if you will, around a given isophote. You can think of an elliptical galaxy isophote as, say, a single period wave as you go in the azimuth. But suppose that there is a twice as high frequency component, then you see two waves as you go around. And there are two possibilities here. One is that they can be co-aligned with major axis and minor axis, in which case they're just going to bump out the isophotes along the axis, and the thing would look like it's got a little lemon-like shape. And these are called disky galaxies, because that's exactly what you get if you were to project together a very thin disk atop of an elliptical isophote. The other possibility is if they're out of phase. And so then you get kind of bumps between the major and minor axes. Those are called boxy ellipticals, and we believe that their shape is due more to anisotropy and less to rotation, whereas disks are always supported by rotation, even if the larger elliptical component is supported by anisotropy. And so here are a couple examples. One of a disky elliptical, and now we think that in fact most elliptical galaxies, those originally classified as elliptical that show this kind of isophotes, lemon-shaped, actually do have disks, and they're maybe closer to S0s than ellipticals proper. But there is a continuum of properties. There are no sharp distinctions. The other one shown is also a boxy galaxy. Some galaxies have both, at different radii. As you go out in radius, what looks in inner part as a boxy elliptical may start looking like a disky one because there is a disk you see at large radius, or the other way around. And so this is not a fundamental distinction like pure spirals versus pure ellipticals. It's more of in the nature of gradual change of the mix. There are some trends that support that there is physically meaningful thing going on, which has to do with velocity anisotropy. The boxy galaxies are more anisotropic. They also tend to be more luminous ones and also have higher extra luminosities. Those can be understood in terms of merging. Random merging of pieces into an elliptical galaxy will both anisotropize its velocity dispersion, and it will contribute to the mass, making them bigger, and can also heat the gas. And so there is a trend. Sometimes people overstate that boxy galaxies are products of mergers, whereas the disky ones are largely products of dissipative collapse. Neither is the case. In reality, there is mixture of those forming mechanisms, and it's just a question of a degree. And next time, we'll talk about internal kinematics of ellipticals.